So good afternoon, everyone. Welcome to our Friday afternoon webinar. Yeah, and this afternoon we are very happy to have Mark Fingerhuth with us. And you all, I think everybody in the call knows Mark. Maybe Omid hasn't met him in person, but probably he's met him in virtually as well. Yeah? Mark did his sort of BSc project with us at UKZN with Maria, and he's the co-author of that very famous paper on the Hadamard classifier, yeah, that kickstarted the machine learning revolution, yeah, and after that. He moved to Toronto, where he took part in the Creative Destruction Lab boot camp, or I don't remember what exactly it is called. The program was a startup program, and after that, successfully set up a company that is called ProteinQure. Yeah, and I think at the moment you are the chief research. I don't remember, Mark, what your official title is, but something like that.
Yeah.
Excellent. And ProteinQure has been very successful, raised many millions of dollars, and but nevertheless, Mark found the time to work on his master thesis, yeah, that he has submitted recently, and today he wants to give us a talk on the content of his master thesis, yeah. And Mark, we set up the webinar as a Zoom meeting, yeah, so that everybody has to make it a little bit more interactive. So everybody has the right to ask questions, and if you are happy at any time, yeah. So Mark, it's your show, so you're most and welcome to start now. You're already sharing your screen, so off you go.
Awesome, cool.
And
thanks, Francesco. And yeah, please feel free to just interrupt me as I'm going through these slides to ask questions, rather than leaving them all the way to the end. So I'm going to be talking about the topic of my master thesis today, which is learning curves of quantum kernel machines. And just quickly about the high-level outline, I had a few things to just introduce myself, about me. Then I want to talk about high-level, what was the research question and the goal of the research. And then we have two things that we need to introduce and kind of talk about first. One is Statistical Mechanics of Learning, about sort of that framework, because that's kind of the framework that we're going to be operating in. And then talk a little bit more in detail about quantum kernel theory specifically, before I can show you some actual learning curves of quantum kernels and give you some examples of how they can be useful, and how you could potentially use them in your work if you're dealing with quantum machine learning models. So Francesco already gave an introduction, so I'm going to skip over that rather quickly. But basically, the summary is here that I am doing a kind of full-time work at ProteinQure, but luckily I've been able to kind of work on a master's program, or like a master's research project during the past 2 years. Fortunately or unfortunately, the pandemic has enabled me to kind of dedicate some more time to that, because I was just sitting at home and there was nothing else to do. And a little bit more than a month ago, I actually submitted this thesis, which I'm hoping to hear back from at some point. But we're going to be talking about the content of this thesis today. And first, kind of about the high-level research question. The idea is that imagine you're given a data set D and 3 different types of quantum kernels, kernel 1, 2, 3. And the question is now to figure out which of these kernels would give us the best performance and the best results without actually just running and executing all these kernels empirically and then looking at the results. So is there a way to sort of theoretically predict the generalization error that we expect from these different kernels in a way that, for example, in this plot, we would see the generalization error of all these different kernels plotted against the number of training examples, which is called a learning curve. And then we would ideally see that kernel 1, for example, is more suited to this data set than the other 2 types of kernels. I'm purposefully not dwelling too much on the details of this plot because we're going to be looking at a lot of these plots later on. But I just want to kind of give you the high-level idea that ideally we would want to have a theoretical way to predict or tell us which of these kernels are better suited for the task. So if we rephrase this, we can say that given the data set D, is there a theoretical or numerical approach to compare the performance of different quantum kernel architectures, allowing us to pick the optimal quantum kernel for the prediction task at hand? And so in order to answer this research question, I first want to talk a little bit about the statistical mechanics of learning, since that's an important ingredient in order to answer this question. So statistical mechanics of learning originates from the field of statistical mechanics, which typically deals with the probabilistic description of complex systems with many interacting entities. So for example, this is usually applied to fluids or gases or other ordered phases of little particles and molecules like electrons, atoms, and other molecules. However, we can apply it also to ensembles of machine learning models, where instead of dealing with an ensemble of electrons, we're now dealing with this ensemble of trained machine learning models, and we can sort of reason about the performance of these models. Usually we're reasoning about the average performance of these models, especially when the numbers of tunable parameters in these models are large. And so historically, this area of machine learning research started around the 1980s. And no surprise, it was started by a group of statistical physicists who were interested in deriving analytical expressions for the average errors of learning models. And so John Hopfield and Elizabeth Gardner were some of the early pioneers in that field. And since then, statistical mechanics of learning has been successfully applied to a range of models, going all the way from neural networks to various optimization algorithms. And so one thing about this field is that initially they started really just using the smallest of toy models possible in order to really be able to kind of tame the equations and be able to derive analytic expressions. But over the years, and especially recently, there has been a lot of progress in kind of moving away from these small, unrealistic toy models to models that are much more closely related to the actual machine learning models that are used today. And one of the hopes is to sort of understand the learning behavior of machine learning models a little bit better, because for most of you probably know that in today's machine learning world, there's a lot of empirical training going on, and people kind of treating these models as black boxes, just kind of tuning the parameters without necessarily understanding exactly why a certain parameter set works better than another. And so the hope is that if we get some sort of analytical understanding of these models, we can kind of open this black box and just kind of understand it a little bit better and reason about its training in a more efficient way. And so one quantity that is very important in statistical mechanics is the thermodynamic limit. So usually, or basically the idea is that average quantities of these ensembles of machine learning models are representative of the model, with the probability tending to 1 as the system size grows to infinity. And so the averages in this case are usually taken over the input pattern distribution. So it's the distribution of all the possible data sets that we could be looking at. And the size of the model defines our input space dimension. And so typically in statistical mechanics, we would take the thermodynamic limit by letting the number of particles n go to infinity, whilst keeping the ratio between the number of particles and the volume constant. And so the equivalent to that in the statistical mechanics of learning is that we're letting n to be the size of the input data, and we let that go to infinity. And v in this case is taken to be the number of training samples. And so we're making sure that this ratio stays constant, but there's also, depending on the paper you look at and the approach, there's also often other types of ratios and quantities that we want to ensure to keep constant as we're approaching this thermodynamic limit. And so interestingly, even though a lot of the conclusions from these papers tend to only apply to the thermodynamic limit, we've seen in a lot of cases that the assumptions or the results actually also hold for smaller data set sizes and smaller model sizes, which is kind of interesting. And there's a lot of work around how to kind of take these limits in such a way that they represent realistic quantities that matter in the real world rather than at the limit to infinity. So for the rest of the talk, we need to define a couple quantities. One important quantity is the generalization error. The generalization error is defined with respect to the weight vector W, and it's basically taking or kind of averaging over the loss given a model weight vector and a data set, and then sort of averaging that over the entire data distribution. This is typically very difficult to compute because the data distribution usually is unknown. And so a lot of statistical mechanics of learning is all about finding expressions that help us approximate this generalization error in a way that we can actually compute it. A quantity that is much more easy to compute is the training error, which is just a sum over the loss functions given a weight vector and the data points within a training data set. In this case, this training data set would consist of m data points. And then overall, given these two quantities, we can say that a trained model is set to generalize if the difference between the generalization error and the training error becomes 0 or is 0 as the training data set size goes to infinity. And so just to kind of outline a little bit of the background or kind of where this field comes from and how you can get from machine learning to statistical physics, I just kind of want to walk you through on a high level through the kind of like the main idea behind this field. So first, we can kind of say that if we train a machine learning model, we want to minimize its training energy by changing the model weights W in some time step delta t. So you can kind of think of this equation as stochastic gradient descent. And then over the years, and so specifically in this kind of household paper by Naftali Tishby, which was one of the early ones in the 1980s and 90s, they basically reframed this equation as a relaxational Langevin equation, where they introduced this potential V, which represents a prior on the weights, and this term eta, which allows us to introduce some noise to the training process. And if you now take this Langevin equation and you evolve this weight vector W according to this equation, it yields us a Gibbs probability distribution given by this equation here, PDW. And so in this Gibbs probability distribution, we also have this partition function Z. And so the way that we can think about this probability distribution, PDW, it essentially tells us the probability of a particular weight vector W resulting from stochastic training. So it's basically saying that given a data set and a particular model instance, if we run the training for 100 or 1,000 times, what is the probability of getting a particular model out of this training? Now, because we're dealing with statistical quantities and statistical mechanics, we need to take the thermal average of the quantities that we're interested in. So let's say you're interested in some quantity A. In this case, then we take the average over PDW, which you can think of as kind of asking it, okay, what is the average quantity A given all the possible models that I could get from training? And so this allows us to kind of reason about the typical average performance of a model given the ensemble of all the possible models. But in this case, we still kind of treat this data set as a fixed quantity. And so that's why typically people in the field also take the average over all the possible data sets in order to be really exact. And so taking these types of averages then allows us to compute the average training error and the average generalization error by, again, averaging over all the possible model weight vectors and all the possible data sets. Obviously, taking these averages analytically is non-trivial, and it requires, in some cases, some very strict assumptions on the data distribution. And the results, as I mentioned earlier, technically are only exact in the thermodynamic limit, but there is a lot of evidence that kind of shows, or a lot of the results have been applicable to smaller data set sizes and smaller model sizes as well. But in general, what you typically see if you look into any paper from the field of statistical mechanics of learning is that in order to tackle these equations, you typically always need to use the replica trick, which is this mathematical trick that a lot of people have mixed feelings about, but historically it just has proven to be useful and helpful in order to kind of manage these equations and deal with the partition function Z. So having kind of given some of the background around statistical mechanics of learning, and I want to talk a little bit about quantum kernel theory before we dive into the results and actually look at some concrete data sets and quantum kernels and compare them with each other. So since I don't quite exactly know what everyone's comfort level is with kernels, I'm sure you've heard a lot about kernels over the years from Maria, but I just want to give a quick introduction again what a kernel is. So a kernel kappa is usually seen as a similarity measure between any two data points. And typically a kernel on two data points x and x prime can be written as this inner product between phi x and phi x prime, where phi is the feature map that maps the data points into usually some higher dimensional feature space. So visually, you can often think about this, it's often illustrated as having a data distribution in 2D, which is not linearly separable, and then using this feature map phi to kind of transform that data into a higher dimensional feature space in which ideally we can find a hyperplane that separates the two classes of data. So that's typically where kernels are used. And popular classical kernels are the linear, the polynomial, the Gaussian, and the Laplacian kernels. And we can now straightforward move this into the quantum realm, where this data encoding feature map phi typically is defined by the way that we are encoding our data into quantum states. And we then compute the kernel kappa of two data points by, again, taking the inner product, but in this case of two quantum states, phi x prime and phi x. And so usually the quantum kernel, as I already said, is kind of defined by the data encoding that you choose. And some of these encodings have some classical analogs. For example, you can see here that using amplitude encoding or repeated amplitude encoding is similar to the polynomial kernel in the classical world. But there's also certain types of encoding, like the time evolution encoding, that doesn't really have a classical analog. And so the hope is that using quantum kernels instead of classical kernels, we can potentially compute kernels that are difficult to compute classically, or we can access very high dimensional spaces, which again would be more difficult to deal with on a classical machine.
Mark, sorry, before you continue, Amira just posted a question in the chat that might be useful to answer for generic understanding. I don't know if you can see it or whether you want me to read it to you.
Now I can see it. I just opened the chat.
Okay, no, perfect. Thank you.
What is the difference between statistical mechanics of learning versus Bayesian learning? I'm no expert on Bayesian learning, to be honest, but generally, I guess the difference is that as far as I understand in Bayesian learning, we don't actually use a lot of the insights from statistical physics. So in the statistical mechanics of learning, one thing that I didn't really go into is that once you get this this Langevin equation and the Gibbs probability distribution, you can essentially start deriving all these physical quantities about your system. So people talk a lot about deriving the free energy of the system, the entropy of the system, and all of these kind of quantities that we typically know about from statistical physics suddenly become important when applying them to machine learning models. And then these quantities like the free energy, for example, again, relates to the training error, the entropy, I can't quite remember what it relates to, but like all of these quantities start having some sort of implication. And so it's much closer to physics than with Bayesian learning, which tends to be, I guess, more of an independent field that doesn't usually concern itself with energies and ensembles of systems. Cool. Okay. So when it comes to quantum kernels, typically we are implementing them in this particular way. So just to kind of show a circuit, so we usually have a data encoding circuit S, which we apply to the data point X first. And then there's this sort of trick of rewriting this inner product of feature vectors as essentially just the application of the data encoding circuit on X, and then followed by the application of the inverse of the data encoding circuit on X prime. And by doing that, we can essentially implement this quantum kernel rather efficiently on a quantum computer. And so one thing that's important to denote here, or kind of separate, is the two distinct ways of creating kernels. There can be stationary kernels and there's non-stationary kernels. And for the rest of this talk, we're mainly going to be focusing on stationary kernels, which is kind of the simpler case, because as you will see in a little bit, the equations become much more manageable in the cases of stationary kernels compared to non-stationary kernels. So what does it mean to be stationary? A stationary kernel kappa can, if it can be expressed as a function of the difference between the two inputs x and x prime, then we say that a kernel is stationary. And so a stationary kernel also comes with the property that it tends to be translationally invariant, but mainly the fact that it can be written as the difference between the two inputs allows us to use some tricks in the equations, as you will see in a couple slides. Another important thing that we need to have in order to put all the pieces together is that every kernel kappa is associated with this Hilbert-Schmidt integral operator Tk, which is defined by this integral. And given this integral operator Tk, we can actually calculate or write down the eigenfunctions and eigenvalues of this kernel integral operator in this kind of way. And so typically we talk about lambda rho and phi rhos as the eigenfunctions and eigenvalues of the kernel, even though specifically they are of the kernel integral operator. But for the rest of this talk, I'm just going to say that these are the eigen decomposition or the eigenspectrum of the kernel. And so we can obviously then plot, given a kernel, we can plot this eigenspectrum. And this is something that is going to be important later on when we start looking and comparing different kernels. Looking at their eigenspectrum will help us reason about their performance given a particular data set. So now that we know that we can get an eigenspectrum of our kernel, we also know that if we have a data set D with m data pairs, x and y, the ideal target function that we're trying to learn is this function f given x should give us y. And now that we have the eigenbasis of the kernel, we can essentially rewrite this equation and express the target function in terms of the kernel eigenvalues and eigenfunctions. And so that allows us to essentially get these so-called target function weights, which are these W's here. And we can plot them again and kind of compare different kernels or combinations of kernels and data sets and sort of plot these so-called target spectra. And these target spectra will again become useful when we try and reason about how a particular kernel and a particular prediction task align or not align. So once again, we call that a target spectrum. And it essentially tells us which eigenfunctions of the kernel the target function puts the most weight on. So for example, in this teal colored case, we can kind of see that these target function weights W tend to be very high for the low eigenmodes, and then they drop off quite steeply and become very small. So this means that these first couple eigenmodes are really important of the kernel, whereas in these other cases, we actually sort of have almost like a uniform distribution over these target function weights. which tells us that even summing over all the eigenfunctions of the kernel still doesn't quite seem to be enough to approximate this target function. So we're going to be talking about that in a little bit more detail. But it essentially informs us which of these kernel eigenfunctions are the most important for learning a particular target function. And in this paper that we've relied on quite a lot by Chanata et al., they essentially decompose the generalization error into a sum of mode-specific errors. So it can tell you for a specific eigenmode, what is the training error that is associated with this eigenmode. And by decomposing the generalization error in this kind of way, we can sort of reason about the alignment between the eigenmodes and the target function in isolation. And that will become quite important down the road. And so one important insight from this paper by Chanata et al., which was applied to classical kernels, is the observation of what is called spectral bias. So spectral bias means that kernel eigenfunctions phi rho that are associated with large eigenvalues can generally be learned with a smaller number of samples compared to eigenfunctions with small eigenvalues. So this is already giving us kind of an important hint that if we can derive the eigen decomposition of a particular kernel, and if we can express the target function in that eigenbasis, given the spectral bias observation, we can kind of compare these two and start talking about which kernels are better suited for a given data set compared to others. And without going into this entire definition, but it brings us to this idea of what's called task model alignment. So given a task, in this case a data set, and a particular kernel or model, we can, as I already said, compare the eigenfunctions and the target function expressed in the eigenbasis. And we can compute this quantitative measure C rho, which typically when we plot it looks like this, which is called the cumulative power distribution. And usually, so in this case already, we have four different types of kernels and 4 different types of data sets. And we can see that only one of these kernels reaches a cumulative power distribution that sums up to unity. And so in this case, this tells us that this particular kernel is very well suited for this particular data set compared to the other ones, simply because of the alignment of where the target function puts its weights and the eigendecomposition of the kernel. Okay, so we're almost done with the theory in order to get to the juicy bits of the results section. But there is an important theorem when it comes to kernel theory, which is called Immersive theorem, which in short allows us to express our kernel in this kind of way, given the eigen basis EK. And so this Immersive theorem guarantees that any kernel can be expressed in this kind of way. And so a big part of my thesis was essentially deriving the Mercer representations of different types of kernels, because once we can write down our kernel in this Mercer representation, we can say a lot about its properties. And so let me skip ahead and give you an example. So concretely, if we're taking a very simple quantum kernel, which simply has one data encoding gate and 2 random unitaries W, and if we kind of go through all of the mathematics, we ultimately arrive at the Mercer representation of this kernel, which in this case also happens to be equal to the Fourier decomposition of this kernel. And this really allows us to kind of look at this kernel and understand which Fourier basis states this kernel supports. And we can then sort of add complexity to the kernel and show that essentially as you're adding more gates and complexity to the kernel, the Fourier basis of this kernel starts growing. And so it essentially allows us to kind of do this Fourier analysis of a particular quantum circuit. And what we've seen, and what I will show you in the results section, is that the more complex the Fourier decomposition of a kernel gets, the more expressive that kernel becomes, and the more functions it can learn. But the last thing that's kind of missing in the toolbox is that the types of models that we will be studying and that we were studying are support vector machines, which most of you are probably familiar with. A support vector machine is a binary linear classifier, which essentially tries to find this optimal hyperplane that separates the two classes of data. And since the data is often not linearly separable in the input space, one of the most popular solutions is to use kernel functions to lift these data points into higher dimensional spaces in order to allow for such a hyperplane to exist. And so in our case, we've focused on so-called quantum classical hybrid SVMs, which are mainly based on the idea of using a traditional SVM. In this case, this is just scikit-learn. We just use this classical SVM, and instead of using a classical kernel, we are plugging in a custom quantum kernel. So the way that you can think of it is that all of the computing related to the support vector machine happens on the classical machine, and only the kernel evaluations, which are computing the similarities between any pair of data points, is performed on a quantum computer, or in this case, in simulation. So we've made it through the theory section. I'm just going to hold off for a second and see if there's any questions, because it was quite dense.
There is nothing. Please, Amira. Sorry, I was just saying there's nothing in the chat. Just go.
Okay, cool. I just wanted to ask Mark, is there like so is it right to say that a desirable kernel eigenspectrum would be like you have a few very large eigenvalues and then no small ones, right? So is that right?
That's typically what we see the Fourier spectra to be like. I would say ideally you would actually almost get like a uniform eigenvalues for all the eigenfunctions, because that way you can combine them in any way and kind of approximate almost any function that kind of fits within that space. Whereas we typically see that the eigenfunctions that taper off on the ends, they don't actually end up contributing a lot to the learning. So ideally we would want to have a uniform distribution of eigenvalues, but it's like I haven't gotten around to design a kernel that actually has such a Fourier spectra.
Okay, because that would have been my next question, but then also something that confuses me. Okay, so that makes sense, right? So like you'd want a uniform distribution, so you have more expressivity, but then wouldn't that also then correspond to like a lower generalization error if you have too much expressivity? I'm sorry, not lower, higher, because you can kind of have this overfitting problem, no?
I guess it depends. As we'll see in the section, it doesn't necessarily, well, like the Fourier decomposition is one property of the kernel itself, but the way that you train the model and sort of like the resulting target function that the kernel represents are kind of distinctly different. So you can get different types of learning out of the same kernel, just depending on like the types of data sets you use and how you do the training. So that's why I would say like the Fourier spectrum itself doesn't necessarily impact if we're overfitting or not. It just sort of tells us something about how expressive that kernel is, and if it can learn a particular function in the first place, or if it lacks the complexity to approximate a function.
Okay, cool. So data has to be,
but it might get a bit more.
Picture.
Yeah, it might also get a bit more clear once you see some of the examples and the results.
Okay, perfect. Thanks.
Sorry, Francesco, did you have a question or?
No. I just wanted to tell you that there was no question in the chat.
Okay.
And then Mira asked your question. So please, Mark, you're welcome to continue. Yeah.
Okay, cool. So maybe I'm just gonna jump over. No, we can't really jump over it. Okay, so basically one big thing that this thesis was about is how do we actually compute these learning curves. It's easy to compute an empirical learning curve because we simply plug in different types of data and plot the generalization error or the training error over time. But in order to compute the theoretical learning curve, Maria and I got very inspired by this paper by Chanata et al., where they derived an analytic expression for the theoretical learning curve, so for the generalization error of, in their case, support vector machines. But they've also derived a numerical algorithm that allows you to compute the theoretical learning curves for these types of models. And they've kind of extensively done some research in the classical world on different types of models, and were able to draw some really awesome conclusions that they've ended to, they managed to also back up by experiments. And so our idea was to take this numerical algorithm and adapt it to the quantum kernel world and sort of change it in such a way that we can apply it to our types of kernels. And so without diving into the details, but they've come up with this algorithm shown down here, which we've implemented, and all of the theoretical learning curves that I will be showing you in the next couple of slides were computed using an adaptation of this particular algorithm. And so because I've been talking about the Fourier decomposition of kernels, when we thought about which types of data sets to use to run these experiments, it seemed natural to rely on Fourier data sets. Simply because if we can, like ideally, we can immediately correlate the Fourier spectrum of a kernel with its ability to learn Fourier series of different degrees. So that made us kind of create these different types of artificial Fourier data sets. And there's two different types of Fourier data sets that we created. The first one is just a straightforward Fourier series based data set, where we essentially have Fourier series ranging from degree 1 to 4. And we call them summed Fourier series because in this case, the Fourier series of degree 4 doesn't just contain the Fourier degree 4, but it actually contains all the degrees summed up to 4. And we also then created what we call pure Fourier series data sets, where again, we go from degree 1 to 4, but in this case, the pure Fourier series of degree 4 only contains the fourth order component rather than a sum up to 4, which allows us to just kind of get some cleaner results in some of our plots later on. So we arrived at this set of 8 different data sets, 4 pure and 4 summed data sets of degree 1 to 4, and each data set had a size of 100 data points. And so the first question that we asked, kind of the simplest question that we can ask is, which Fourier data sets can a single qubit quantum kernel learn? So this kind of shows the most simple, or one of the simplest quantum kernels you could potentially write down. The random unitaries of this kernel are simple Hadamard gates, which are sandwiching this RZ operation, which is just the parameterized by the difference between the data points. So just to kind of bring in some of the things that we talked about earlier, this kernel clearly is a stationary kernel because it can be written as the difference between the two data points. It contains it's made out of a single qubit, and it probably doesn't have a lot of, or a big Fourier spectrum. So if we look at the generalization error, which is now the empirical one, so we're not computing any theoretical learning curves at this point, but we're simply looking at how the generalization error behaves as a function of the training data set size P, we can see that for these 4 different Fourier data sets, 1 to 4, we only see learning happening in the case of the data set of Fourier degree 1, which isn't very surprising because we're dealing with a very simple single qubit kernel, but it's kind of nice to see that kind of result because it seems like these Fourier data sets of degree 2 and higher just are too complex for the single qubit kernel to learn. But so let's look a little bit under the hood. So first here on the left side, I'm plotting the eigenspectra the eigenspectrum of the single qubit quantum kernel. And on the right side, we see its Fourier spectrum. So the single qubit kernel has a very simple Fourier spectrum. It really only has one, like the frequency, the first order frequency component, as well as the zero order one. And kind of this immediately allows us to kind of relate that back, because the quantum kernel only has a single Fourier frequency in its Fourier decomposition. It is only able to learn a Fourier data set of degree 1, simply because it lacks the additional complexity. Which is also shown if we look at the target spectrum, which we were discussing earlier, which again, to remind you, is expressing the target function in terms of the kernel eigenbasis, where we can see exactly what I mentioned earlier, that for most of the data sets, summing over all the eigenfunctions still isn't sufficient to actually approximate these data sets. Whereas in the case of the degree 1 data set, we have kind of a high concentration in the target coefficients for the low eigenfunctions, and then very low target function weights for the higher eigenfunctions. And then we can plot this cumulative power distribution, which is this measurement for alignment between kernel and data or learning task at hand. And this is exactly what we're seeing. We're actually seeing kind of a nice separation between them. First of all, the data set of degree 1 sums to 1, because we're able to actually perfectly learn that. And it means that there's a high alignment between the task and the model. And then it kind of goes down where like the degree 2 data set and the model have less of an alignment, followed by the degree 3 and the degree 4 data set. So none of this is really a surprise. It's just kind of nice to see it broken down in that kind of way, and see that sort of the compatibility between the kernel and these different data sets drops off as the degrees or the complexity of the data sets increases. And then ultimately, this is a plot that kind of overlays the empirical and the theoretical results. So these dashed dotted lines result from this algorithm that we've adapted to the quantum kernel world, which you can see kind of up to some scaling factor accurately predicts that this single qubit kernel will only be able to learn the Fourier data set F1 compared to all the other ones. And it's important to note here that this theoretical curve was computed without actually running any experiments, and is then confirmed by us running the empirical experiments afterwards. So a more interesting question to ask now would be that, given a more complicated data set, in this case, the summed Fourier data set of degree 4, and different types of quantum kernels with different numbers of qubits, we can ask the question, how many qubits do I need in order to learn this F4 data set? And so that's something that we analyzed, where we looked at the Fourier spectra of kernels that range from 1 to 4 qubits. And you can see that we've been looking at the 1 qubit case, where we only get the first order component. As we're adding a second qubit, we're unlocking the second order component. And so with each additional qubit, we're getting one additional Fourier frequency that the kernel is able to use in order to approximate certain functions. So looking at this plot, to kind of loop back to Amira's question, you kind of see how it tapers off quite drastically. And ideally, we would not want to see it tapering off that much, because now having this like very small eigenvalue on the fourth order frequency makes that frequency accessible, but knowing about the spectral bias of kernels, the Fourier, or in this case, the Fourier and the eigenbases are the same. The ones with high eigenvalues are easier to learn, which means that even though we have these higher order frequency components, they are still much more difficult to use or to learn for the kernel. But yeah, so then we can look at the eigenspectras of these different types of kernels, and we can see that the more qubits we add, the bigger or the more complicated, the richer this eigenspectrum gets. And similarly, when we look at the task model alignment again, we can unsurprisingly see that as we're adding more qubits, we're getting better and better alignment between the kernel and the data or the learning task, but none of them sum up to unity, which means none of them are able to learn the data set until we actually added the fourth qubit, and only then have we reached like the necessary expressivity of the kernel in order to learn this fourth order data set. And then again, we can look at the theoretical compared to the empirical learning curves, and we see that the theory matches the experiment and accurately predicts that we would need a 4-qubit quantum kernel in order to learn this data set. Yet another question that we can ask is, again, taking this fourth order Fourier data set, what unitaries should we choose for our kernel in order to learn this data set more efficiently? So we tried 3 different types of random unitaries. So we kept the encoding the same, but then we tried rotational unitaries, non-sparse unitaries, as well as sparse unitaries, which we just used tensor products of Hadamard gates. And we were kind of trying to understand how that introduces complexity or expressivity to these kernels. So once again, we can look at the Fourier decomposition given these 3 different types of random unitaries. And we can see that, for example, in the rotational case, we barely get these higher order frequencies. Whereas if, for example, the non-sparse unitaries allow us to kind of increase the eigenvalues of these higher order frequency components, allowing us to kind of access them in a more convenient way. Which, without showing you all the other plots again, is again kind of predicted by our theoretical learning curves. And we can interestingly see that these rotational unitaries, and we've kind of seen that across the board, tend to lead to lower expressivity, and kind of in a lot of cases, these kernels fail to learn the more complicated data sets, whereas using sparse and non-sparse unitaries actually lead to successful learning. So all of these types of analyses and these types of questions that I was just highlighting kind of brought us to compile this analysis toolbox for quantum kernels. So because now we essentially have these various analysis tools and ways of kind of looking under the hood of a kernel that allow us to kind of tweak and modify a kernel in advance before actually running it to make it more compatible with our data set at hand. So without going through all the individual steps of this toolbox, they basically kind of summarize a lot of the things that we've been looking at on the previous slides, analyzing the target spectrum, the eigenspectrum, looking at the Fourier spectrums of these kernels. And you could then kind of envision a world where you're given a data set, for example, MNIST, and you can then go and sit down and sort of design a custom kernel or take an existing kernel and modify it in a way that it will have the expressivity and the complexity required for the task at hand. So in terms of some of the future work that we were proposing, and some that we're actually even working on ourselves, is mainly investigating the generalization performance of non-stationary kernels, because all of the results that I was showing are limited to the special case of stationary kernels, because some of the equations simplify. But we would ideally like to unlock the non-stationary case, because that would make this toolbox and this technique much more widely applicable. We would also like to kind of understand how the number of embedding layers in a quantum kernel impacts the generalization performance, rather than just looking at the random unitaries and the number of qubits. And then kind of going away from these artificial Fourier data sets and applying this toolbox to actual real-world data sets, such as MNIST, given different types of quantum kernels. And then also kind of looking at some of these equivalences between quantum kernel machines and quantum algorithms that are trained on data, such as QAOA and VQE, if we can kind of use some of these insights from the quantum kernel world in order to reason theoretically and analytically about these types of algorithms like QAOA and VQE, which would kind of, I guess, help us open that black box as well and understand how their learning behavior changes. So overall, brings me to my conclusions. The statistical mechanics of learning allows us to compute the average generalization error of different learning models. we successfully adapted a numerical algorithm for theoretical learning curves to quantum kernels. And we showed that it helps us to accurately predict the learning behavior of stationary kernels. And we compiled this toolbox for quantum kernel analysis, which you can use for kernel design, given a particular data set. And it essentially allows you to measure the alignment between a given learning task and a machine learning model. It provides, or we did provide, code to numerically calculate these theoretical learning curves. All the code is available open source on GitHub. And we're currently working on a publication for which we want to crack this non-stationary case first, and then ideally hoping to submit that by the end of the year. So that brings me to my almost last slide. I wanted to say a big thanks to Francesco and Maria for all their help and support and just making this master's degree possible in the first case. It's been an amazing experience. And also thanks to Nelly and Info, who helped me navigate some of the crazy UKZN bureaucracy over the years, and I'm very thankful for that. So thanks for listening, and I'm happy to answer any kind of questions or hear any kind of comments that you might have.
Yeah, Mark, thank you very much.
I don't understand.
Ah, sorry. Siri liked your talk and is talking to me. Sorry. Thank you very much, Mark. It was really an excellent, excellent presentation. And as you said, there is still some work to be done in the non-stationary case, but we will get there eventually. Thank you. Are there questions for Mark?
Well, there's a question in the chat. Nice graphs. Is there any special software tool package that you use to produce them? Well, the special software tool is called LaTeX. I painfully plotted everything using LaTeX, but I feel like it's really rewarding because you actually get these very clean looking graphs rather than making them somewhere else, screenshotting them and then pasting them into your thesis. So it's a little bit of upfront pain, but it's quite easy once you set it up.
But is there a special package that you use in LaTeX for that, or is it just hardcore LaTeX?
It's just, I think, the TIX picture package.
Yeah. Okay. Yeah. So essentially hardcore LaTeX. Yeah. Fantastic. Okay, that was a technical question, an aesthetic question. Are there some more technical questions for Mark?
If nobody else has, then maybe I can ask again one more.
Yeah, please Mark. Go ahead. Yeah, please break the silence. Yeah.
Yeah. So sorry, I still I don't fully understand a few things. That's probably just my naivety. But so firstly, the case that you guys analyzed, of course, is just like with one layer, like one embedding and encoding layer. I mean, one embedding, and then the variational layer is pretty. You consider these three scenarios, right?
Yes.
Okay, and then like based on certain things, and you can kind of show the distribution of the frequencies you have access to, and like kind of translate this in terms of the eigenspectra language, right, or framework. And so now, like, what I'm wondering, of course, okay, like firstly, do you have an intuition for some sort of strategy that could perhaps create a richer spectrum, right? Because that's ultimately what you want, is just something with a rich spectrum. And then also like, but then on the other side, I thought that, so let's go to the other case where you repeat embedding layers. I thought that in Maria's paper, they kind of show that then you have access to more frequencies. This increases like based on the number of repetitions of encoding. But I also thought that this was bad for generalization error for some reason. I thought that this like impacts there's like some point at which you would overfit. I mean, there just kind of has to be, right? So I guess I'm a bit confused with these two pictures. So maybe we can start with the first thing is like, do you have an intuition for a design that would maybe produce a richer spectra? And then I'll try and explain the second part better.
The short answer is I don't have an intuition what would make a richer design. It's one of the things that we're hoping to still derive for the paper, is sort of, can we come up with an expression that tells us, that directly relates the Fourier spectra to the choice of circuit? So for example, like, okay, depending on what kind of unitaries or encoding gates I choose, how does that impact the Fourier frequencies or the kind of the magnitudes of the Fourier coefficients, and sort of having an expression that relates these two things would allow us to then kind of come up with an intuition and sort of easily plug in different unitaries or different encodings and then see how it directly impacts it. And that way you could design something custom. But we haven't come up with this expression yet. And then, I mean, yeah, right, like we were restricted to these single layer kernels because of this stationary, the special case of looking at stationary kernels. Once you start introducing the multiple layers, you're getting into the non-stationary territory, where Maria has derived the Fourier decomposition of, but what we are unable to do right now, and what we've been working on, is sort of trying to figure out how can we now go from this Fourier decomposition to the Mercer decomposition, which you need to have these kind of, you have to have a mapping between the two in order to allow the type of analysis that we did. And that's currently still an open question. Once we are able to figure that out, the hope would be, again, to come up with an expression that directly relates the Fourier or the Mercer representation of that kernel to the choice of circuit elements, which would help you to kind of create that kind of intuition. But right now, we pretty much just kind of came up with this way of like, okay, this is how you can think about quantum kernels, and you can analyze them given this framework. And we're hoping to kind of get some intuition out of that ultimately, but right now we don't.
Yes, okay, that perfectly answers both parts. So yeah, thank you.
Yeah.
Thank you, Amira. Thank you, Mark. Are there further questions for Mark? So suggestions, comments? Mark, it looks.
Okay, maybe, sorry, I have one more. I have one
go.
more thing to say, but this is not a question. Maybe it's just a suggestion. I'm so sure that Maria has probably like mentioned to you already, Mark, but I think it would be interesting for you to check out. So I don't know if you had a chance to watch Peter Bartlett's talk, Posner lecture at was it Europe's, Ilya? I can't even remember. From late last year, and he kind of speaks. It's not about kernel spectra, but he kind of speaks about linear models, and they talk about the spectra of something a little bit different, but I think slightly similar, but they call it this data covariance matrix and what this would look like. And I think this is like really close and interesting, and could be like a different angle or approach to try and analyze the more general part. I mean, I know that the whole benefit of what you're doing is that the Fourier stuff gives you a nice method or toolbox to like analyze things theoretically. But if you don't, if you're not able to do this in the non-stationary case, there could be maybe something else to approach. And this beautiful theory that was developed by Bartlett and a few others is, I think it's very easily translatable to the quantum side, but then one just has to figure out what kind of circuits again translate to a rich spectra, but not of the kernel, but of something called the data covariance matrix, which I think is very, very similar. So yeah, maybe check out that talk and ask Maria about it, because I know she watched it, and I think maybe it's relevant for like this idea.
That's awesome. Could you put the name of that guy into the chat by any chance?
Oh yeah, sure.
I just didn't quite catch the name, but that sounds
I
interesting.
can, and the link to the talk if you have it.
Yeah, I
Yes,
can probably find that, but that would be very helpful. Thanks for that.
Yeah, sure. Let me see if I can also pull up the link. If we wait a few minutes, I can also get it, because
Okay.
I think
otherwise
I have.
I'll follow up with you afterwards.
Okay, yeah, sure.
No, thank you, Amira. Thank you very much for that. And is there anybody else that has comments, suggestions, or other links that are relevant? Literature? No, Mark, it seems everybody are happy. Then Mark, thank you so much for a very nice talk and what is a very nice thesis as well. Yeah, let's hope that the reviewers come back to us in the next few weeks, because now they had it already for a little while. Yeah.
Awesome.
And yeah, and Mark, thank you very much for your time. I know that it's probably quite early for you in Toronto. So thank you very much for probably having skipped breakfast to be with us. Yeah, and yeah, no, and I hope that that we will see you again soon. Yeah, and hopefully we will interact to complete the famous paper with the more general case. Yeah, that it's still keeping you busy. Yeah.
Yeah.
And I'm sorry that Maria didn't join us, but maybe was busy with something else. I don't know. But we will send you the link to the video once it's uploaded on YouTube. Yeah. So
Sure.
Mark, thank you very much for your time, for the nice talk, for sharing the LaTeX secrets of your graphs, and for the nice summary of the master thesis. And yeah, and thank you very much for all of you. I think we were almost a full house today, which doesn't happen very often. So Mark, thank you very much for bringing the whole group back together in one go. It means that it was really an interesting topic to everyone. Yeah.
Awesome.
So thank you, Mark. We stay in touch, and yeah, and keep warm, because you told me that it's again cold in Toronto.
Yes. Thank you very much, everyone,
Okay,
for attending, and thanks for sharing the link, Mira. I just saw it in the chat.
Thank you very much. Thank you. Have a good good day. Yeah. Thank you very much.
Bye, everyone.
Bye bye. Bye bye.